Greetings and welcome to Mr. Van Lowe's poorly monetized, low-budget science channel. Do not click like, do not subscribe. Okay, we're going to get into the second lesson for topic 7.1 here. Okay, the first lesson has not been recorded yet, so as soon as I do record it, I will pop it up. In the meantime, let's look at our lesson objectives for lesson 2. First, by the end of this lesson, you'll be able to describe the properties of alpha, beta, and gamma particles. You will understand isotopes. You will also be able to describe radioactive decay, including background radiation, and work with radioactive decay equations. Finally, you will be able to briefly describe the fundamental forces between particles. Okay, so to begin, we're going to need some definitions here. First, a nucleon is either a proton or a neutron. Protons and neutrons have nearly equal mass and size, but neutrons are slightly more massive, just a little bit. Nuclides are a nucleus with a specific number of nucleons. Z is equal to the number of protons in a nucleus, and you may have heard this referred to as the atomic or proton number. A is the total number of nucleons, meaning both protons and neutrons in a nucleus, and this is called the mass or nucleon number. N is the number of neutrons in a nucleus, and this is equal to A minus Z, which of course is the mass number minus the number of protons. So next up we have nuclear charge and notation. So the charge of any given nucleus is given by Z times E, and recall that Z is the proton number. So we're multiplying the number of protons by the fundamental charge. Okay, so and this is a positive number, so we have a positive charge on the nucleus. Okay. Note that the electrons for a given nucleus will cancel this charge out. So our atom will have a net charge of 0. So if you're wondering why this is positive, that's why. Okay, nuclei are described using the following notation, where we have X being our element, and we have A up here and Z down here. So the larger of these two numbers will always be the mass number. Okay, so the larger number will always be our mass number A. Okay, so here are some examples. We have uranium-238. Okay, and we know that it's uranium because it has 92 protons, and all isotopes with 92 protons are uranium. Okay, this is how we define an element. Okay, the number of neutrons, you'll recall, is calculated by subtracting this smaller number from the larger number, and that gives us, in this isotope, 136 neutrons. Okay, another example, very common, hydrogen. Here we have a hydrogen nucleus with 1 proton and 0 neutrons. Okay, we also have helium here. We have 2 protons and 2 neutrons, and we're going to come back to this because this is also exactly the definition of an alpha particle. Okay, we can also apply a similar notation to nucleons, where protons become a little p with a 1 here and a 1 here. Okay, so we've got our nucleon number and our mass number. Okay, neutrons become 1 and 0. Okay. Actually, sorry, this should be a charge, not a mass. Okay, so we've got charge in the lower left. This really should be up here. Anyway, moving on. Here we have electrons as well. So we have the mass number, the charge number, mass number, charge number. Okay, mass number, charge number, mass number, charge number. Okay, so our protons have a charge of positive 1e, and E, of course, is equal to our fundamental charge. This is in your data booklet on the first page. Electrons have a charge of negative 1e, giving a negative charge. No surprises here. When we're referring to nuclei, we just simplify all this by saying that protons have a charge of +1, and electrons have a charge of -1, and neutrons have a charge of 0. And we'll look at these charges in a little bit more detail later in topic 7, when we start looking at quarks and other fun stuff. All right, so let's look at isotopes. So in isotopes, we'll get to isotopes in a second. First, let's look at our fundamental particles here. So we've got a proton here with a mass of 1 and a charge of 1. Here we have a neutron, mass of 1, charge of 0. Electron, mass of 0. It's actually not 0, but for our purposes here, it's about this 1,000th of the mass of a proton and neutron, so we just round it off to 0. And our charge is -1. Okay, a positron, which is the antiparticle of an electron, has a mass of roughly 0 and a charge of +1. We have a photon then given by mass of 0, charge of 0, and this symbol is, I believe, lambda, and so this is, no, I'm sorry, gamma. And gamma, of course, is also a type of radiation, which we'll talk about a little later. Here we have an alpha particle, and again, that looks just like a helium nucleus, or it could be denoted by alpha, and then our mass number and our proton number. Neutrinos have the same notation as a photon, although these are very different particles, as we'll see later. And our antineutrino is a bar V, as you can see here. So there's the whole table. Normally I wouldn't read out a whole table, but there's some interesting stuff going on there. Okay, so if we look at isotopes, they will have the same proton number, but they're going to have a different number of neutrons. Okay, so what this tells us, as we touched on earlier, is that elements are defined by their nuclear charge, but not by their nuclear mass. Okay, so next we're going to talk about radioactive decay, and this is where things start getting weird and cool. So we've covered all the stuff that you probably already know. Now let's get on to some new stuff. So most nuclides that we encounter are unstable, and that means they're going to both randomly and spontaneously emit particles. So that brings us to this word, radioactivity, which you have certainly heard before. Okay, so radioactivity is just the emission of particles and energy from a nucleus. Simple as that. We have 3 types of radiation. There are alpha, beta, and gamma. Woo woo. I was right. That is a gamma. Okay. Each type will have a different ionizing power, penetrating power, and that's it. Okay, so ionizing power is the ability to knock electrons off of atoms, and our penetrating power is just the distance traveled through matter before the radiation is stopped. Okay, so let's talk about alpha decay. Alpha decay is where an element emits an alpha particle and becomes another element with a smaller atomic mass and number. Okay, so an example of this would be uranium decaying into thorium and 1 alpha particle. Okay, and here's the equation for that. And note that this equation looks exactly like a chemical equation. Okay, so we have our uranium nucleus here, and it is spontaneously decaying into thorium-234 and helium, our alpha particle. So if we look at the mass numbers here, they should correspond. So we subtract 4 from 238, and that gives 234. We subtract 2 from 92, and that gives 90 here. So basically, all of our particles in this example are conserved. In other words, we don't have any mass disappearing. Okay, and as we've discussed, our alpha particle is identical to the helium nucleus. So we put uranium into a box and we find thorium, and we also find this weird gas. So you collect the gas and you do a spectral analysis of the gas, and what you're going to find is that the gas is helium. Okay, so, and we've already talked about spectral analysis in our previous lecture on topic 7.1. So there you go. Okay, so beta minus decay looks a little bit different than our alpha decay. So, incredibly, this involves a neutron in a decaying nucleus turning into a proton. And in this process, it emits an electron and an antineutrino. And later on, at the end of topic 7, we're really going to take a look at this decay, and we're going to diagram it using Feynman diagrams, which is pretty fun. Okay, so an example here would be thorium nucleus decaying into protactinium. Say that 5 times fast. Okay, so here our thorium nucleus from our previous equation now becomes something new. Okay, so the mass stays the same. Whoa, crazy. But the element changes. And again, that's because our neutron is becoming a proton. Okay, so that's going to change the charge on the nucleus, and it therefore becomes something new and different. Okay, note again that our mass is conserved. Okay, so we've got 234 here, 0 here, 0 here, so 234, 234. So if you look at the left side of the equation and the right side of the equation, everything is conserved. Also, if we look at our proton number down here, you'll note that charge is also conserved, and we'll talk about that a little bit later. But for right now, just keep that in your head. So our beta minus particle is just an electron. Okay. So now we have 2 types of radiation. We have alpha, a helium nucleus, and beta minus an electron. Okay, cool, done. Okay, here's another example. Here we have lead becoming bismuth, I believe. And again, our mass number stays the same, but our proton number increases by 1. We also emit an electron and an antineutrino. Okay, so this is a beta minus decay. You're going to need to be very familiar with it. Now, you might have been wondering what is going on here. This chart just shows the neutron number over here and the mass number over here on the x-axis. Okay, so what we have here is this very important line here where we have stable nuclides. These nuclides no longer decay. Okay, they're just going to stay whatever element they are. But note that this is a very small band of isotopes. Most isotopes fall outside this stable range, and that means that these are going to be undergoing decays or potentially fission up here when we get up to the really high numbers. Okay, so our reds here are beta plus decays, and our blues here are beta minus decays. So an element that has this particular neutron number and this particular mass number is going to undergo a beta minus decay. Okay, and we know that eventually that's going to happen, although we don't know exactly when. We can calculate when it might occur in terms of statistics, but we can't predict exactly when. Okay, probably should have explained that slightly earlier, but anyway. Okay, so our beta plus decay is where a proton in the decaying nucleus turns into a neutron, and this emits what is called a positron and a neutrino. So again, a positron is the antiparticle of an electron, and it has the same characteristics as an electron except a positive charge. Okay, and we'll talk about antimatter a lot a little bit later. Okay, so an example of this would be beta plus decay of sodium and nitrogen. Okay, so here we have our sodium. Actually, this is becoming, yeah, so our sodium is becoming neon. Okay, again, our mass number stays the same, but our proton number is changing. Okay, and we have here our positron, or anti-electron, if you prefer, and our neutrino. Okay, so same relationship here, same thing happening. Okay, next up we have gamma decay, and this is where a nucleus emits a gamma ray. And a gamma ray is just a photon of high frequency electromagnetic radiation. So it has a very small wavelength, but a very high frequency. So an example of that would be uranium emitting a gamma particle. So that's it. No mass change, no change in the charge. So what we're left with is a nucleus that looks just like the old nucleus, except it's lost a bit of energy. Okay, so there you go. So the wavelength of our emitted light will be given by wavelength, or lambda, being equal to Planck's constant times the speed of light divided by energy, and we will have covered this in our previous topic, our previous lecture on topic 7.1. So there you go. Here's a summary of the characteristics of radiated particles. I don't want to read the whole table for you because you can probably work it out yourself. These mass values are in your data booklet. Penetrative power is not in your data booklet, okay? And it is important that you know this. So our alpha particle only travels a few centimeters into air. So our alpha particle can literally be stopped by a piece of tissue paper. Beta minus particle requires a few millimeters of a metal of some kind, okay? It will penetrate further through other stuff, but as we know, metal is a good conductor, and that's going to interfere with the passage of our electron, which again is a beta minus particle. So these particles are moving quite fast, as you might have surmised from this. Okay, our gamma ray is going to penetrate through many centimeters of a very dense metal, lead. Okay, so alpha particles can ionize about 10,000 ions per millimeter of air for a 2 mega electron volt particle. So this describes the kinetic energy of the particle. Okay, so alpha particles have the greatest ionizing power in comparison to the beta minus particle and gamma particle. And again, you probably want to know these values as well. How can we find our various particles? Alpha particles, well, all of our particles will affect a photographic film. Our alpha particle is affected by electric and magnetic fields. Our beta minus particle is also affected by electric and magnetic fields, but our gamma ray is not affected by these fields. So there you go. Uh-oh, I've got some bad animation here. Depressing. Okay, anyway, so let's look at what is called a decay series. So this refers to the changes in atomic and mass numbers of a nucleus when it undergoes radioactive decay. And what happens is we keep getting more decays until we get a stable nucleus. Okay, so in this particular example, we have neptunium decaying into, no, this isn't titanium. I'm not actually sure what this is. Fantastic. Thallium. Lucky. So neptunium decaying into thallium, and now I've got a huge mistake here. I'll fix, you know what? I'm just going to do it right now. We don't edit, guys. We just don't. Okay, done. So we have First, our neptunium undergoing an alpha decay, and then a beta minus decay, and then another alpha decay, and then another alpha decay, and then a beta minus decay. And for each one of these decays, it's becoming a new element, as you can see, or sometimes becoming kind of repeating the element, as we'll see down here. So anyway, this process kind of continues until eventually we're just down to our thallium, which is now our stable isotope. So, and it has to be exactly this isotope, or it's not stable. Okay, so we have thallium 209 here, and this is still going to undergo decays, but thallium 205 is stable. Okay, again, alpha decay, this produces an element of a lower mass. Beta minus decay produces a new element of the same atomic mass, but different proton number. Okay, so as we suggested earlier, radioactive decay is random and spontaneous. So we need some definitions here. Random means we can't predict which nucleus in a sample is going to decay or when there's going to be a decay. And spontaneous means that we can't affect the rate of decay of a given sample in any way. And this is really kind of weird, both of these things. So we have to use statistics to figure out how a sample is going to behave. We can predict the we can predict the rate of decay, however. So the rate of decay is proportional to the number of nuclei that have not yet decayed. So here we have our change in nuclei divided by our change in time, and this then is proportional to the number of nuclei. Okay, so exactly what we've stated here. Okay, so here we have the radioactive decay of thallium into lead. And the half-life is the amount of time after which the number of radioactive nuclei is reduced by a factor of 2. Okay? So in this chart here, our half-life is about 3 minutes, or 180 seconds. Okay, so it's just the amount of time. Every 3 minutes, or 180 seconds, our sample size decreases by 1/2. Okay, so this is quite a fast rate of decay. Okay, so the number, yes, we've covered that. Yes, we've covered that. As the amount of thallium decreases, the number of lead nuclei is going to increase, and that's going to produce this interesting curve that is directly related to this curve. So if we take our total number of nuclei at the beginning and we subtract from that number the amount of these thallium nuclei at any given point in time, we're going to get the number of lead nuclei. Okay, so after our first half-life, we'll have exactly the same number of lead nuclei as thallium nuclei. Okay, so this is always going to be our halfway point on our graph, and it's pretty important that you are able to identify this point, because when you are asked inevitably to draw the number of new nuclei on here or vice versa, this point will be key in determining that. Also, if you go across here, you're going to find that your number of new lead nuclei will approach this number over time, although it may take a very long time for it to get there due to the nature of exponential decay. Okay, so here we have activity, and activity is the number of nuclear decays per second. The unit that we use for activity is called becquerel, and 1 becquerel is equal to 1 decay per second. And activity obeys exactly the same exponential decay law as the number of nuclei. And here, so we'll work some problems in our handouts related to activity and the number of decays, because they're closely tied together. Okay, so here we have radioactive decay and background radiation, because we're constantly surrounded by background radiation. And disappointingly, it is never mutating us into superheroes. Sorry, it just doesn't work that way. So here we have the decay curve of an isotope. And this is a bit of a problem because if we want to find the initial number of isotopes or the initial activity, we need to figure out a way to get rid of the background radiation. So how could we do that? You can pause the video now and think it over or discuss. And I will sing the Jeopardy theme song. Dun, dun, dun. Okay, that's enough. So you've now considered how to find the level of background radiation. All we need to do is subtract. We have a horizontal asymptote here. If we subtract this number, actually this graph is slightly problematic, but anyway, if we subtract roughly this number from our graph, then we get the actual number of decays per second or activity. Okay, so we just find that horizontal asymptote, subtract it from the graph, the y-axis, and now we have our actual sample's decay rate. Okay. So fundamental forces, this is the last one, and bizarrely they just tacked this onto the back of topic 7.1. I'm not quite sure why, but anyway, let's talk about the standard model briefly. First, we have a number of interactions, and we're going to talk about these in more detail later in topic 7, so you want to pay attention. You need to be able to define these. So electromagnetic interaction acts on any particle that has electric charge. And as we've already discussed, some of our particles do not have electric charge, such as neutrinos or electromagnetic radiation. Okay, so the force given for the electromagnetic interaction is given by Coulomb's law and has infinite range. The weak nuclear interaction acts on protons, neutrons, electrons, and neutrinos in order to bring about beta decay. It has a really, really, really short range. So what that means is that our neutrinos need to travel very close to our nucleus in order for this to occur. Okay, I have a link here to a YouTube video. Maybe I will share it with you later. Okay, the strong nuclear interaction is a mainly attractive force acting on protons and neutrons to keep them bound to each other inside nuclei. This also has a very short range, 10 to the negative 15 meters. As we know from topic 5, protons are positively charged and should repel from each other. Okay, the reason why they don't is the strong nuclear interaction. They're bound because most nuclei are within this very short range. But as you can imagine, as your nuclei get larger and larger, perhaps getting larger than this value, then the strong nuclear interaction isn't going to be enough to keep your element together anymore. And this is exactly why larger nuclei tend to be very unstable. Okay, gravitational interaction. This is a force of attraction between masses. And the small mass of our atomic particles makes this force irrelevant for atomic and nuclear physics, and this force has infinite range. It is also one of the biggest problems with the standard model because, well, for reasons we'll discuss a little bit later. But note that gravitational interaction is a huge, huge problem for physics. Electromagnetic interaction and weak interaction are two sides of a single force, which we call the electroweak interaction. And that is going to be it. Here are my sources. And there you go. Thanks for watching. Do not click like. Do not subscribe. You have been listening to Mr. Van Lowe's low budget, poorly monetized science channel. Have a good day.